Counting is something that we have been doing since the days we were in first grade. From counting sheep before you fall asleep, to counting the number of students in the class and counting the number of vehicles that go down the road, we have used the concept of counting for different aspects in our day-to-day life. And in this video, we are going to see how counting plays a major role when it comes to statistics and when it comes to determining the probability and whatever the other calculations that you do, especially when it comes to statistics and mathematics. So in this video, we're going to discuss about some special rules that we use here in statistics when it comes to probability theory. So we have a few different counting techniques, such as the addition rule, the multiplication rule, the arrangements, permutations, combinations, which will all be discussed during this video. So if there are any doubts, do feel free to reach out to us through the comment section, or else you can check the group description for a detailed translation of all the terms, all the important terms that will be needed during this video. So, in many problems of statistics, we have to count and we have to find the number of outcomes. So when we come to do this, we have to know how many observations exactly we have, or else how many predicted observations that we can have. So all these observations can be counted in different techniques, and those techniques are what we are going to discuss today. So without further ado, let's see what the first rule of counting techniques really is. So now we have the first rule that we are going to learn about, and that's called the addition rule. You will see that this addition rule is not much different from the same old addition that you have been doing throughout your school life. So suppose you want to find the decision about what to wear to university. Well, yes, you are in university now. And if we have a lot of clothes, the decision would be more difficult. It's simple, right? Because the more things you have, the more that you have to count. The concept here is that things that we are counting are on the same level. Consider this example. It says PL cannot decide what to wear, whether it's a t-shirt or a shirt. He has 4 t-shirts and 2 shirts. So he has 4 t-shirts and 2 shirts. Now can you see that both of these are on the same level? What do I mean by the same level? It means they can't wear both the t-shirt and the shirt together. Well, that would be weird, right? So it could either be a t-shirt or a shirt, which makes all these options into the same level. So he has a total of 6 choices, which amounts up to 6 because there are 4 t-shirts and 2 shirts. And that's how you do the basic counting when it comes to the addition rule. It's pretty simple. It's the same old addition that you have learned during school days. But you will see the amount of wonders this does as we advance further and go into the other counting techniques as well. Now, let's move to the next counting rule that we have. And now we have multiplication rule. This multiplication rule is just an advancement of the addition rule. Let's continue with the same old example that we had with PL in our discussion. So now, apart from the t-shirt, he also has a choice for the denims or the trousers, what he's wearing for the bottom. So now let's see how many choices he has for a complete outfit. So he has 6 choices of t-shirts or shirts, which we know from the previous example. And he has 3 choices for denims. Now look, they are not on the same level. There are 6 tops and 3 bottoms. Now each of these tops can go with each of these bottoms. So we cannot say that there's only one suit matching. No, he has all those choices and we have to think what are the choices that works best for Pia. And it's pretty straightforward for us to think that 6 times 3, which is 18, is the number of options that he has. So this is where we unknowingly use the multiplication rule when we do things in our day-to-day life. Even when we multiply a simple thing just to find the multiplication of two numbers, without knowing, we're using the multiplication rule. Now you see, even in our day-to-day activities, statistics plays a major role, and without knowing, we are using the multiplication rule and most of the other counting rules during our day-to-day life as well. I hope it's starting to make sense to you now. Then it brings us to the third counting technique, and we have something called arrangements. Think of the literal meaning of the word arrangements. An arrangement is putting something into a proper order, into an order that we can understand and we can make things sensible. So when it comes to arrangements, there are different ways that we can arrange things. Think of you arranging your room or maybe arranging the table that you have before you study. So imagine there are things that you want to put in a line, say a set of pens, or think of a queue, the number of people that are in a queue. Or just as we say in this example here, the number of ways of arranging the letters. These four letters can be pens, can be people, anything. So in this example, we have the number of ways of arranging the letters A, B, C, D is 4, and there's a little exclamation mark at the end. So what is this exclamation mark exactly? We'll look what it is now. That is called the factorial notation. What is the factorial notation? This is just a technique that's used in mathematics when we have to multiply a number by all of the numbers that come before it, preceding numbers. So if we have 5 factorial, that happens to be 5 times, 4 times, 3 times, 2 times, 1. And if we have 7 factorial, it's going to be 7 times, 6 times, 5 times, 4 times, all the way up to 1. So all these numbers play a huge role in making all of these long multiplications into a cluster. So that is why the factorial notation is used. Now, why does this factorial notation come here when we do arrangements? That is the question that we have now. So, think of it this way. For now, consider these 4 letters and think that you are hoping to arrange them in a straight line. You have 4 letters and you have 4 boxes or 4 spaces that you can fill those 4 letters into. How exactly are we going to fill these boxes? That is the question that we are answering. Now think, there is no proper order. It doesn't say to put A at the front or B at the front. So we can put whatever the letter we want to whatever the place that we need to. So we have 4 places and we have 4 letters. So let's take it one step at a time, one box at a time. Then to the first box, we can add either A, B, C or D, which leads us to 4 different options. Say we put A, but I'm not just doing it because it's the first letter. I'm just putting one of the letters, which means when you go to the next box, we have 3 letters remaining, B, C, D. Say I put C here. Then when we go to the next box, there's only 2 letters left. And when we go to the last box, say you put C here, say you put D here, you put A here. And when we come here, there is no choice but to put B, which brings us to one of the arrangements that we have. This is not the only arrangement. Just like this, we can ADCB, ABCD, ACBD in any order that we want, which amounts us to 4 times 3 times 2, which is 24, which in other words is 4 factorial. Why? Because it's the multiplication of 4 by its preceding numbers. So this shows us how this factorial notation makes our computations so easy, and how this factorial notation actually comes into play when it comes to an arrangement of objects in a line. Now always remember, if we have things in a line and the order does not matter, which means we do not have to care which one comes first, which one goes next. We just have to put in the numbers in a way that we have to fill up all the slots. The way of arranging in unlike objects in a line, that happens to be n factorial. So now we have done that and we can flip them around. So we have 24 different ways we can do that. And that's how we arrange things in a line. And note that these objects have to be unlike. These letters are not the same. What if they are the same? Well, let's find out. So sometimes we might come across situations where repetition is allowed or some letters are alike. Let's also think how we can tackle such a situation if the repetition was allowed. If n different objects were given repetition and also we were asked to put them in order. Let's think of the smallest example. Let's think of the same example that we did. Now ABCD can be put in 4 different places and ABCD can be repeated. So for the first box, we can have 4. For the second box, we don't have to get rid of A. We can still use one of the 4. We can still use one of the 4. We can still use one of the 4. So we have 4 times 4. Or in other words, 4 into 4 into 4 into 4. And what if we have 5? We will have 5 times 5 times 5 times 5. So does this ring any bell? Well, yeah. This is n to the power n, which means 5 to the power 5, 4 to the power 4, and there are n to the power n types of combinations or types of arrangements that we can make when repetition is allowed. However, if repetition is not allowed, we can only have n factorial type. So let's see if repetition is not allowed, but still there are some alike objects in the arrangement that we are hoping to make. How can we tackle such a situation if that ever comes up? Well, the answer is not so far away. Now, we have things that we need to store in a line, but what has happened? P of those are alike. Well, why exactly P? Well, let's find out. They say the number of ways of arranging 5 marbles, including 4 blue marbles and 1 red marble, is 5 according to the answer. But how does it become 5? Well, let's find out. They're telling us there are 5 marbles altogether, 4 blue marbles. Let me draw the 4 blue marbles. 1, 2, 3, and 4. And there is 1 red marble. Now, if we want to arrange these in a straight line, this is just one way we can do this. This is just one of the ways. Just like this, we can have the red ball in another place, can't we? We can have the red ball here, we can have it here, we can have it here. But now imagine you switching this blue ball here and sending this blue ball here. And then in the next one, you keep the red ball here and you do the same thing with the blue ball. This goes here and this goes here. Think, does it make any difference? Both these images look the same. Well, it looks the same to me. What about you? Well, that means there is no point in changing the order of the blue balls because it does not make a difference because all these 4 blue balls look alike. Then if we have things that look alike, we do not need to consider all of it. We can either subtract one at a time. So since there are 4 different things, we know there are 4 different ways we can arrange these people. So we have to divide by that number to get rid of it. Very simple. So what we do is we take the total number of arrangements that we can have, which is n factorial, which we learned in the previous part, and then divide it by the similar people so that we get the final answer, which is the way that you can arrange n objects of which three objects are alike. And we can simply give the answer as 5 factorial over 4 factorial because 4 blue is happening. But without knowing, we are doing something here. Even though it says 5 factorial over 4 factorial, without knowing there is a 1 factorial as well. I will explain more about it to you in the next part. And also, when it comes to the factorial notation, there is a given concept which says 0 factorial is equal to 1. Just keep that in mind, because that might come into play later on. Now the next result tells us more about arranging objects of which some types are alike. Now it's not just one type that is alike like the previous one. Now we have 2 or 3 types that are alike. And we are going to arrange the letters in the word statistics. If you think of the word statistics, we have S, T, A, T, I, S, T, I, C, and S. There are 3 S's, 3 T's, 1 A, 2 I's, and 1 C. 3 S's, 3 T's, and 2 I's, as it says. Now, we are hoping to arrange these letters in a way that we can make different words. So, as you can see, 3 letters are alike, 3 letters are alike, 2 letters are alike, which means we cannot just divide by one of the things because we have different types that are alike. And the concept says we can first take the total number on top and divide by each of the extra types in the bottom. And without knowing, once again, 1 factorial is there. But since it's equal to 1 by default, we don't need to write it. So altogether, we have 3, 6, 7, 9, and altogether 10 letters. Out of these 10 letters, we have 3 alike, 3 alike, and 2 alike, which gives us the total number of arrangements that we can make is 10 factorial, which is n factorial, divided by 3 factorial, 3 factorial, and 2 factorial. And this will be our final answer, which happens to be 50,400. How do we do those calculations? Just write 10, 9, 8, 7, 6, all the way up to 1, divided by 3, 2, 1, 3, 2, 1, 2, 1, which is 3 factorial, 3 factorial, and 2 factorial. Now we can cancel out things in a way that it makes sense. Here we have 5, 4, 3, 2, 1, and 3, 2, 1. 3 times 2 is 6, and 3 times 3 is 9. In a suitable way, you can cancel them off. And you will see that everything falls into place, and you will finally end up getting 50,400. Do make sure you double check your answers. Now let's look at the fourth result. Here, a hint of multiplication rules comes into play within the arrangements. What has happened? If an operation consists of 2 steps or multiple steps, of which the first can be done in n1 ways, and for each the second can be done in n2 ways. So n1 and n2 are processes of either result 1, result 2, or result 3. It's basically just one arrangement. And now one arrangement happens right after the other. Just like we chose a t-shirt and then a trouser. So how can we do that when it comes to arrangements? We are going to learn in this result. So let's consider the first example. It says how many different item codes can be formed if each is to contain one of the 3 letters, contain the 3 letters A, C, E, not one of the 3 letters, contain all 3 letters, followed by the 4 digits 4, 7, 8, and 9. And also make sure that repetition is not allowed here. Even in the previous examples that we considered, repetition is not allowed. So, if it is supposed to be an item code, it has to be unique, right? Which means the letters that we have here and then the 4 digits that we have here should be unique for one another. So, the digits alone can do something on its own, and then the digits. First the letters all alone and then the digits. Now check. If we Let all the 7 of them mix together, then letters will be in the middle of, in amidst the digits. It should be quite chaotic, and that's not how we not want our item code to be. That does not serve our purpose. So, if we are to do this properly, we should first consider the letters, then consider the 4 digits. So first consider the letters. We have A, C, E. So there are 3 different options that we have. So for the first box, we can have 3. Second box, we have 2. Last box, we only have 1 choice because repetition is not allowed. So we have either A, C, E to each of these places, which gives us the final answer. Yes, you guessed it right. 3 factorial right here. And in the same way, now you don't even have to think of the concept because the concept has gone into your mind and you know there are 4 different digits here. 4 different distinct digits, which can be arranged in 4 factorial ways. And then there are 3 factorial t-shirts, 4 factorial trousers. Altogether, we have 3 factorial times 4 factorial, which is 144 because 3 factorial is 6 and 4 factorial happens to be 24. 24 times 6 is 144, which gives us the answer. Voila. Then let's consider the second example. The second example says, how many different item codes can be formed if each is to contain the 4 letters A, C, C, and E? I say a repetition. And the 6 digits 4, 4, 7, 8, 8, and 8. I say repetition once again. We don't have to panic because we know when repetition is allowed, you just take the total number divided by the number that has been repeated. So the first process, which is the 4 letters. We have 4 letters altogether divided by the number that's repeating. C is the only thing repeating and it's repeating 2 times. Then we go to the next process. We have 1, 2, 3, 4, 5, 6 digits and we have to divide by the repetitive parts. We have 2 fours, 3 8s. We're not dividing by the number because we are dividing by the count of the number. So we have 2 factorial times 3, which gives us the final answer. 4 factorial over 2 factorial happens to be 4 factorial is 24 divided by 2 times 6 factorial happens to be 720. But we don't need to write it that way. Let's use some shortcuts. We have 6 times, 5 times, 4 times, 3 factorial. Does that make sense to you? Because right after this, it's 3, 2, 1, which is same as 3 factorial. And we can cancel this off very happily now. And then this 12 remaining here. Here we have 2, which means 2 times 2 comes here, right? Then we have a 10 here. We have 12 times 6, 72. 72 times 10 is 720. And we get the answer once again. Did you see how we can use the factorial term to cancel out multiplications pretty easily? And this is how we do the multiplication rule, one process after the other. And result 4 is no big deal for us now anymore. Then brings us to a very important concept, which is called circular arrangements. So far, we were arranging things in a straight line. All those barcodes, all the item codes that we had, all of them were in a straight line. So now, what if they were in a circle? What difference does it make? I want all of you to put your imagination shoes on as we think of this. When it comes to a circle, compared to a line, well, it's a circle compared to a line. What difference has happened? This edge has gone towards the other edge, and that's how we have gotten this circle. Well, we can think of it that way. And the best way to think of a circular arrangement is to by considering an example and putting yourself in this example as well. So we have 4 people, A, B, C, D, who was to be seated at a round table. Now you are a part of A, B, C, D. Don't forget that. And if we wanted to make these people just sit on a straight table or on a table that was in a straight line, we'd have 4 factorial different ways, wouldn't we? But it mentions that circular arrangements have a quite peculiar result. Why is it weird? That's what we are going to figure out. Imagine you go and sit. So there's supposed to be 4 different seats that you can take your seat in. If you sit here, you have one option here, one option here, one option here, one option here. So does that mean you have 4 different options to sit there? Think of it for a second. Well, it does not mean you have 4 different ways to sit because we have to have distinct arrangements. If you sit here, say in the seat that's right here, if you sit there, what happens? You can see one seat to your left, one seat to your right. But say you had a different kind of a day and you went and you sat here. Well, one seat to your right, one seat to your left. No difference. Because relative to you, there's no difference in taking the seat. So here in the first box, we only have one choice. I hope that makes sense to you. Always put yourself in that position because whatever the place that you sit out of these 4 in the first moment itself, it does not have any impact on the rest of the people until you take your seat. Why do I tell that? Now tell you have already sat here. X is already here. And we need 3 different people for the other 3 seats. Now there is only one seat that's on your left hand side. This seat is not on your left hand side, this seat is on your right hand side. So this is for one person, and this is for the other person, and this is for the last person. Can you see that there are different ways that we can make the others sit? So it doesn't have to be this way, it could be this here, and this here, or it could also be, or it could even be this here, and this here, in whatever the way. That means to the second box, we have 3 different ways that we can put. And to the next box, we have 2 different ways we can put. And to the last box, we have only one way that we can arrange. Which brings us 3 factorial ways. There are 4 seats in a circular table, 3 factorial ways that we can sit. Which tells us if there are n objects, we have n minus 1 factorial ways we can make them sit on a round table. Keep that in your mind. And now we reach another important concept in circular arrangements, which is arranging things in a ring. Now, what does it mean to arrange things in a ring? As opposed to a usual circular arrangement that we considered in the previous example, which is like arranging things on a table, now in a ring, what happens is you can turn it around. If you can turn it around, you can't just sit on a table and look from the other side. That doesn't make sense. But if it's a ring, you can flip it and there will be 2 different arrangements that look exactly the same. Which means if we have A, B, C, D like this, and we twist this around this axis right here, and we look at it this way, A and C will not change. D and B, however, will change. Are these 2 different objects? But are these the same arrangement? But they look different. So how do we consider that? We have to divide by 2 factorial once again, because for each symmetry, there are 2 different ways that we can twist it around. So it happens to be n minus 1 factorial, which is just for the circular arrangement of one side. You divide by 2 factorial, or just straight up 2. That's the concept of circular arrangements, arranging objects in a ring. And that brings us to the 4th counting technique that we are going to consider, which is a very, very important one. And now we have permutations. So permutations are much like arrangements, but a bit different. Let's read and see. Frequently, we are interested in situations where the outcomes are different ways in which a group of objects can be ordered or arranged. What do we mean by the different ways in which a group of objects can be ordered? I want you to always imagine a photograph whenever you think of permutations. You just think of the ways that you can take pictures in a way that the people will sit in separate ways. How many ordered arrangements? That's another word that we use for permutations. How many ordered arrangements are there for the letters A, B, C? Well, we might have to find out. I have 9 paintings and I have room to display only 4 of them at a given time. So you are in a shop, maybe you want to put up 4 paintings, but you have 9 of them with you, but only 4 places. And those 4 places can change for each of the people. And you also have to do that difficult choice of choosing only 4 paintings out of the 9 beautiful paintings that you have. So those are called ordered arrangements. You choose people, then you have to arrange them in the place that you have to do. Then a permutation is an arrangement of all or part of a set of objects with regard to the order of the arrangement, with regard to the order, which is a very important concept. Now let's see. There is an easy concept when it comes to permutations that you can always refer to. And that formula says NPR is equal to n factorial divided by n minus r factorial. So what does it mean to say n factorial over n minus r factorial? Well, let's see how it happens. P stands for permutation, n stands for the total number that you have, r stands for the number of items you have to choose. It says all or part of a set of objects, so NPR. And it says divide n by n minus r factorial. Well, where does this come from? Out of the blue? Well, we are not used to doing it that way. Let's try to understand what the concept behind this is. We have n different objects, and from the n different objects, we have to choose r. So if we are doing that choice, say we have n different objects, and all these are different, by the way. And out of these, say we have 5 for now. Out of these 5, we have to choose 3. Say I choose this, I choose this, I choose this. So I have chosen 3. I can arrange these in a way that I want. But I can't do anything about the other 2, can I? This and this. They are the same to me now. They are not considered, which makes them objects that are alike. And you see how the arrangement technique comes to play in permutation formula as well? So, without knowing, we have taken all 5 objects, which is 5 factorial, and divided by the number that remains after we take the people that we need, which is 5 minus 3, 2 factorial. 5 factorial over 2 factorial, which is 5p3. Does it make sense? Just as NPR becomes n factorial divided by n minus r factorial. I hope how this concept, how this formula was derived makes sense to you. And now you can do any question that you had at the beginning. And let's see how to solve these 2 examples that we have considered here. Now let's see how many ordered arrangements or permutations are there for the letters A, B, and C. So 3 letters, 3 ways to arrange. So all 3 objects out of 3 are unlike. So we have 3 different things. So we have a base NPN sort of situation because R is equal to N, which tells us n factorial divided by n minus n factorial, which is n factorial divided by 0 factorial. Here also it mentions, I told you earlier as well that it will come into play later. 0 factorial is 1 and n factorial. Altogether, the answer becomes n factorial. And does this ring a bell? Yes, it should. That was the basic concept we learned of arrangements. So the permutations of ordered arrangements of distinct objects, which is just an arrangement, is n factorial. Pretty simple, right? It all makes sense. Now, we go on to see how many ordered arrangements are there of 2 letters from the letters A, B, C. just two letters now. So from the three letters that we have to make the difficult choice of choosing two, and then we have to arrange the three. So we have 3 factorial divided by 3 minus 2 factorial, which is 3 factorial divided by 1 factorial, which is also 1, which is 3 factorial, equal to 6. Very, very simple. And if you do not understand the concept, no worries. You have to always go back and think of the original scenario. We have 3 different objects, out of which we choose 2, and then the rest of the objects remaining are no longer our consideration. So we divide by 1 factorial. I told you when we were doing objects alike arrangements that we divide by 1 factorial without knowing. A similar situation has happened here as well. Can you see all these techniques that we have in counting are interrelated to one another? And it's just the same technique that has been used in different concepts with a little bit added every single step that we take. Now we'll see how many 5-character passwords can be made using the letters A through Z. So we have 26 letters and we have to only choose 5. So it becomes 26P5. Looks like a pretty daunting calculation. We have 26 factorial divided by what? 20? 21 factorial. Why? Because 26 minus 5 happens to be 21. Cool, let's see. So when we are subtracting this, we don't need to do the top and bottom separately. We can write this as 26, 25, 24, 23, 22, 21 factorial, then divided by 21 factorial, because we are not going to divide by the same thing. Now just take the multiplication of these numbers and you will see that the number amounts up to 7,893,600. Now here's another example which is more practical. 24 members from a club, and we have to elect a president, a vice president, a treasurer, and a secretary. So out of 24, we have to select 1, 2, 3, and 4 positions. So we are selecting the members randomly. We are not considering anything. So we have to consider the total number of choices. So out of the 24, we have to permute 4 different positions. Why do I have to permute? Because we can change within the roles as well. After we get the president can be one person, and that same person can go to vice president, and the vice president could be the president, because they have to be distinct one another, obviously. So we have four different ways that we can permute in between. So when it comes to the concept, it's 24 factorial divided by 24 minus 4, that is 20 factorial. So it's gonna be 24 times, 23 times, 22 times, 21 times 20 factorial, which gets divided by 20 factorial over here. And then once you multiply the numbers all together, you will end up with 255,024. 24 into 23 into 22 into 21. Pretty simple. Once again, another example. How many different item codes can be formed if each is to contain 2 letters out of A, B, C, D, followed by 4 digits out of 1, 2, 3, 4, 5, and 6. And we have multiplication rule inside permutations. So we have to contain 2 letters out of the 4 letters that we have at first. So we have 4 letters out of which we have to contain 2 letters. And these 2 letters that we choose can have the same and can flip around in between as well. So it's a permutation. And then you have to multiply that by the digit part. Out of 6, we have to choose 4, and we can permute in between as well. So 4p2 into 6p4. 4p2 happens to be 4 factorial divided by 2 factorial. 6p4 happens to be 6 factorial divided by 2 factorial as well. So this becomes 12, because 4 factorial is 4 into 3 into 2 factorials. 4 into 3 is 12. 6 factorial divided by 2 factorial is 6 into 5 into 4 into 3 into 2, which is 360. So 360 into 12 happens to be, yes, 4,320. And that's your answer for this question. That brings us to the last counting technique that we have for this video, which is combinations. So what is a combination? As opposed to a permutation, a combination is just the selecting process. Remember that you wanted to select 4 pictures out of the 9 that you had? So this is just considering the selecting process, which means you can no longer think of what you're going to do in between. That means after selecting the pictures, you can't flip them around. So let's see how we calculate those things as well. A combination is a selection of all or part of a set of objects without regard to the order. So without regard to the order goes without saying that this happens to be something like selecting a theme. Call it selecting a theme. Just like you wanted to think of photographs for permutations, I want you to think of selecting a theme. A theme every time you think of a combination. Because when it comes to a photograph, you can flip the people around and take different photographs. But when it comes to a team, flipping the people around in the team and taking a photograph doesn't change the team. It's going to be the same team. So now we're going to have an additional r squared in the division, which is the permutations that you can do within the selected team itself. And once again, we are not used to accepting the things as they are. We have to work out and see how it happens. So let's see how NCR notation is used. C is for combinations. N is the total that we have. R is the number that we want to choose. Say we have 5 people. Once again, the same old example. 5 people, and we want to select 3 out of this. I'll have a dot here, I'll have a cross here, I'll have a line here, and I'll have a Y here, just like last time. I select 2 out of this. And now this is my team. Like I said, it does not matter what the order they stay. So 2 factorial ways, but I do not care. So I have to divide by 2 factorial here. Here there are 5 different people, so I have 5 different ways that I can get the team. But out of that, 2 people were chosen and 3 different people are left. And they are the same to me now. They were just not selected, unfortunately. So they can be arranged in 3 different ways. The people who were selected can be arranged in 2 different ways, which we are not going to consider this time. So divide by it. Once again, arrangements where some objects are alike and we divide it. And that gives us 5 factorial over 3 factorial over 3 factorial into 2 factorial. Which means if we generalize the concept of NCR or the permutations, we have the concept which says n factorial divided by r factorial, which is the chosen part, divided by n minus r factorial, which is the part that we could not choose because they are on the same level, because they are nothing but a team. So we have to divide in a way that the permutations don't adapt. So there is a short notation for this, which we call combinations. So let's dive into another example. Say one might inquire in how many ways we can select 2 letters without an order from a set of 3 letters. Now we're just going to select. We don't need to care about the order. We are not making an item code of any sort. So complete list of possible selections would be just A, B, A, C, and B, C. How does that happen? Out of 3, we choose 2. So it's 3 factorial divided by 2 factorial into 1 factorial, which is 3 divided by 2, 3 into 2 factorial, then that gets cancelled, just 3. So we have the 3 options here. Whenever you get stuck, think of the smallest example that you can have. Just like I did with this, always think of a small example and you can grasp the concept easily. Now here look, AB and BA are considered to be one combination. Just like I said, these are 2 different members in the same old team. So the selected order does not matter. So now that we know a bit about combinations, now let's see what the connection that we have between combinations and permutations, because by now you might realize that both of these notations look quite similar in NCR and NPR. But what exact difference does it make between themselves? So we have NCR and NPR. Now think, I told you that combinations are like selecting a theme. And when it comes to permutations, permutations is like taking a photograph of the team in different positions or changing the positions of the players in a team. Now, can you imagine which one is bigger? Combinations or permutations? Well, it should make sense to you that permutations are almost always bigger unless we take the whole combination itself. But think if you have to, by some point, take the combinations and then take the permutations, which is the underlying concept that happens. How would we consider that? We had n objects, out of which we had to select R, and then we had to arrange in between the R, which means we had to multiply by R factorial, which would give us NPR. Do you see that this notation comes true? How does that happen? NCR, by notation, we know this is n factorial divided by n minus R factorial into R factorial. And we know that NPR is n factorial divided by n minus R factorial. Can you see the only difference is this little R factorial? That's the one who's doing all the difference in here. And that is the number of arrangements that we can have within the selected objects, within the selected subset to be exact. If the subset happens to only have one object, then we're going to have a combination that's equal to a permutation, which means we're not doing any permutations. We're just selecting one person. So you can see the connection between the combinations and permutations very easily after this. So NPR can be written in other words as NCR times R factorial. Now let's work out some more examples on combinations so that we can actually grasp the concept really well. So this time we are playing with a deck of cards, and out of the 52 cards that are in the deck, we have to select 4 cards. We only have to select. See, we don't have to all think of the arrangement of the cards. We just have to select 4 cards out of the random, which means out of the 52, we have to select 4. We have to combine. All combinations comes into play. 52 factorial divided by 4 factorial divided by 48 factorial. Can you see? 52 times 51 times 50 times 49 times 48 factorial, and I'm not going to write any further. Divided by 4 factorial times of 48 factorial, which gets cancelled off. And if you do the math, you'll see that the answer becomes 270,725. Very easy. And in the same way, if we are to find the number of ways to select 4 letters at random from the word randomly, then we have 1R, 1A, 1N, 1D, O, M, L, Y, which means all the 7 letters in randomly are distinct to one another. That means we don't have to divide by any similar or repetitive terms, which would have been the case. So now it's just a straight up combination. So out of the 8, let us select 4, which is 8C4, 8 factorial divided by 4 factorial divided by 4 factorial. So the answer becomes 8765 4 factorial, 4 factorial, and the other 5 factorial I will write as 432 because I know only one of them will get cancelled out. I can see 765. 3 times 2 is 6. I know that. 4 times 2, isn't it? And that gives me 7 times 2 times 5, which is 14 times 5, and the answer becomes 70. And the last example that we have. Find the number of ways to select 4 letters at random from the word randomly, which are consonants. So 6C4, why? It's 6, and you just have to select 4 letters. 6C4. But why is it 6 now? It should have been 8. Because we have a filter. The filter says only use the consonants. So we no longer have access to O, we no longer have access to A. R, N, D, M, L, Y are still in the game. So we have 6 in the game. Select 4 out of it. So it's 6C4, which is 6, 5, 4 factorial divided by 4 factorial times 2 factorial. It's divided, that is 3. 5 times 3 is 15. So now we know how addition, how multiplication, and arrangements, permutations, combinations come together and help us solve our daily problems that we come up when we pursue our field in statistics. We can also see how addition and multiplication serve as the base, as the foundation for everything, and how arrangements and permutations, combinations are built on that, and the same concepts go underlying every single time. So whenever you do these sums, I suggest you to always make sure you understand the concept before you try attempt the questions and not just blindly use the formula. Thank you for watching.